so let's go ahead and get started. As you guys know by now, I'm Zach. I'm one of the TAs for this class. I hope finals have been going well for you and you had a nice weekend. Okay, so I got a couple emails about things to do, so we're just going to start with a couple questions from those. But do we have any big picture questions before we get started? And reminder that you can ask in the chat, you can turn your mic off and ask, whatever works best for you. In the chat, other students may also answer. But anything I do and say will be recorded and posted. I'm not totally sure if the chat gets translated, but I'll say everything as I do it. Okay. So the first question I was asked is question 19 on the practice midterm or practice final. Okay. Okay. So a little bit of review about what eigenvalues are, what they mean. Why isn't this working? You guys can see my screen, correct?
Yes.
Yes.
Cool. All right. Why isn't this there? Okay. A little bit bigger. So what an eigenvalue is. So the definition of an eigenvalue is well, there's a bunch of different definitions for it, but the big one is if you have a matrix A times some vector V, and it's the same thing as some number times V. Okay, so essentially, like when you multiply A times your vector, it's the same thing as a number times your vector. That number is your eigenvalue. Okay, what that means is when you do, or equivalent to what that means is when you do A minus lambda I, okay, the determinant of this is always going to be equal to 0 due to the characteristic polynomial. And what that means is A minus lambda I will always have a free variable. So having a free variable, just as a little bit of a reminder, is the same thing as having the dimension of the null space of the thing we're talking about being bigger than 0, okay? So in this case, what we're looking for is when we subtract A minus 5i, we want a free variable at least, okay? That if that is true, then it is an eigenvalue, okay? If this is true, like if A minus lambda I has a free variable, then lambda is a eigenvalue, okay? So for the sake of this, we're going to assume that it is. All right. All right, find a value case such that this is true. So essentially what we're doing A minus lambda I, which is equal to A minus 5i, okay? So we have 6, 1, k, 2, 6, 3, negative 1, 0, 4, minus, remember I is the same dimension, by 5, 5 on the diagonal, 0 is everywhere else, okay? And we write this equal to 1, 1, k, 2, 1, 3, negative 1, 0, 4, okay? So what we're trying to find is such that this has a free variable, okay? How do we do that? We find out if these rows are similar in any way, shape, or form. That's the definition of what this means. So when we row reduce,
the bottom right is negative 1, right?
With
oh,
bottom right,
my bad.
yeah.
I took the 5 minus negative 1. That's my bad. So our goal is when we put this in reduced row echelon form, it's going to look something like this. Where these two numbers, one of them can be 0, but they can't both be 0. Okay, we want a free variable, right? All right, so how on earth do we do this? Well, when in doubt for a matrix in this class, you row reduce. Okay, so, oh god, I'm going to make a fool of myself trying to do this. I'm going to move the bottom row to the top and multiply it by negative 1. Okay, I'm going to keep my middle row the same. and I'm going to combine my first and third rows. So I get 0, 1, k minus 1. Okay? Cool. Do you guys see the row reduction going from here to here? Is that like clear? I know I'm not writing every single like row operation as it happens, but I switched first and third, and I combined. I put the third one where the first one was, and then I added the first one to the last one. Okay. So from here, we row reduce again. 1, 0, 1. We're trying to get rid of this 2. Okay, so how do we do that? We do R2 minus 2, R1. Okay, so that'll be 0, 0. And what's that? 3 minus 1, 2. No, that's just 1. I got that wrong. Minus here, that's not 0. Okay, so 0, 1, k minus 1. Okay. So we're here right now, and we want it to look like this. Okay. So what does that mean? If we have a free variable, okay, remember that means our rows are similar to some extent. So right here, what you can note is like these bottom 2 rows right here look very similar, right? And if they're the same, when you row reduce, they're going to go to a 0 row, okay? Just think like if you have like 1, 0, 0, and you have 0, 1, 1, 0, 1, 1, these 2 rows here are going to cancel out, right? One of them is going to go away when you row reduce, all right? So what does that mean? It means we have to have 1 equals 1, okay? Like going from here to here, and it means 1 has to equal k minus 1. So that means k equals 2. Okay? So reminder that the reason that we knew that these things had to be equal is because these 2 rows had to be similar to each other, okay? If this was like 2 and 1, okay, then whatever we do, we have to divide this top one by 1/2 when we try to equate them, okay? Questions about this? If you guys can mute yourself when you're not asking questions, that'd be fantastic. Can I do that from here? Oh, I can.
Yeah, I had a question. So, what do you say about the 1/2?
About the what?
You said something about the 1/2 somewhere.
Yeah, so like if this matrix, like instead of it being like a 1 and a 1 right here, like if this was a 2 and a 2, essentially what that goes to say is we want that like first number to be the same, okay?
Okay. So the whole point of this is, make row reduce so that you have at least one non-pivot. So that's how you know it's
a free variable. A non-pivot is the same thing as a free variable.
Or what if you have more than one, or it has to be at least one for it to be?
It has to be at least one. Okay. If it has more, that means you have geometric multiplicity. Okay. For a minus lambda I. On that note, a quick note about diagonalization, because I know you guys have struggled with this, and that is totally fair and valid, and it is a very confusing thing to talk about. So, just some notes on diagonalization. Diagonalization, you have A equals C, D, C inverse, if and only if A is diagonalizable, okay? That's what this double F means. If and only if. It just means the 2 things are the same thing, right? You can break down A like that if it's diagonalizable. If it's diagonalizable, you can break it down like that. Okay, same statement. So remember that D is just equal to all of your eigenvalues on a diagonal, okay? Right? And your C is just equal to each of your eigenvectors, right? Cool. So how do we know if it's diagonalizable? Well, you have like, let's call this an n by n, right? So how many eigenvalues do you have? N, right? Note that this is not n distinct eigenvalues, okay? They do not have to be distinct, okay? You can have one multiplicity of n, right? You can only have one as an eigenvalue, but it can occur algebraically n times, okay? So for something to be diagonalizable, all matrices always have n eigenvalues, but for it to be diagonalizable, it has to have n eigenvectors. Okay, this makes it diagonalizable. That is the only condition. Okay, that means the same thing as for each lambda. Okay, if Algebraic multiplicity equals the geometric multiplicity for respective eigenvectors, it is diagonalizable. Okay, because like think about it. If you don't have enough eigenvectors, you can't fill up this matrix, right? And if you can't fill it up, you have no idea what it is. All right, does that make sense? I saw a question about, there are a handful of questions in here. All right, so I see going over column A, row A, null A, how they can be related regarding orthogonalization and inverse. I'll do that because that's a little, we'll start with that and then we'll do complements and projections. Yeah, so algebraic multiplicity. Algebra is numbers. Geometry is a graph, okay? So if it has a geometric multiplicity, that means when we have like a minus lambda I, okay, it gets us, well, for some v, when we're looking for our eigenvectors, right? So remember, whatever this is, how we find it is we find, like for this matrix up here, we'll take it to be 1, 0, 1, 0, 1, 1, 0, 0, 0, okay? Let's say this is a minus lambda I, okay? 4 lambda equals 5, multiplicity of 1, okay? Eigenvalues are numbers. They are in algebra. They have algebraic multiplicity. Vectors are geometric. They exist in space, so they have a geometric multiplicity, okay? Geometric just means how many like vectors you get from your null space of a minus lambda I, okay? So, this v is our eigenvector. This is how we find it. We take a minus lambda I for whatever lambda, okay? We find this matrix here, and this form right here is the null space, right? Well, we're not going to call this A. We're going to call it a hat, okay? V equals 0. So we're looking for the null space of a hat. That is, whatever that is our whatever those are our eigenvectors, okay? So how do we find that? Parametric form. Well, before that, you write it in equations, then parametric form, and then you just take your vectors. So for this one here, we have x1 plus 0x2 plus x3 equals 0. We have 0x1 plus 1x2 plus x3 equals 0. And we have x3 equals x3. Okay, because x3 is a free variable, right? So from here, we rearrange it so that we solve for the lowest subscript, right? x1 equals minus x3, x2 equals minus x3, x3 equals x3, right? These are our equations. And to get from here to parametric form, you just slap some brackets on it, like that, right? Because this gets us x vector equals x3 v1, okay? So this is, we take out an x3 from this vector here, minus 1, 1. So this vector is our eigenvector, okay? Cool. So in the instance that instead of this we had something like this plus, like for a different matrix, if we had this plus, I don't know, 0, 1, well no, we'll call it 1, 1, 0, okay, x2, this has how many vectors? 2. That means this lambda has, well, this lambda's eigenvectors properly, because a lambda doesn't have geometric multiplicity. multiplicity of 2. That's what that means, okay? When you take this and you find however many vectors, that's its geometric multiplicity, all right? And if your algebraic multiplicity equals your geometric multiplicity for all your lambdas, i.e. if you have as many eigenvectors as eigenvalues, then it's diagonalizable. Okay, so that is diagonalization. We're going to talk about, very quickly, we're going to do range domain and codomain, and then we're going to talk about the null space, column space, and then the perpendicular components or the orthogonal components, and then we're going to go into projections and stuff. Okay?
Good question. Will you be posting these notes anywhere?
Say that again?
Will you be posting these notes anywhere?
I can send the PDF when I send out my recording.
Sounds good. Thank you.
Yep. Cool.
Oh,
so,
sorry.
Mhm.
I have another question really fast. Why would the null space have a dimension of 2 in the example you just
it
showed?
doesn't. I just, like, right here, I just changed it to, like,
okay.
if it was a different matrix. Okay?
Oh, okay. Sounds good.
Yeah. Great question. Little confusing. But, yeah, this is, like, discontinuous to this. Okay? This is just me saying, like, oh, hey, if we, in the case that we had 2 vectors, that would have a multiplicity of 2. Okay? Got it. All right, moving on. So range domain and codomain are a little bit simpler. So is it m by n matrix or is it n by m? I always forget the notation for this class.
It's m by n.
I believe it's m
by n. Like that. M by n. Cool.
Yes.
I always confuse me all the time. I get mixed up with that stuff. But regardless, so A is m by n. So let's call A m is rows, n is columns. Okay? So from here immediately, we know the domain is Rn. Okay? That's where we start. That's where x lives. All right? Domain is where x lives. Okay? Codomain is R to the m. Okay? This is where B lives. Okay? It's not the space that you can get to for B. It's not the column space. It is just like, how many entries does B have? That is our codomain. Okay? Our range is R to the rank of A. Okay? So however many linearly independent vectors we have, that is the space we create, right? So like say dimension or rank of A equals dimension of column space of A. Let's say it equals 3. Okay? And let's say m equals 6. Okay, so the way you can think about this and like how we thought about like for the first exam is what would A create? It would create a 3D space in R6. Or the way I like to notate it, it'd create an R3 space technically, but I just write it would create an R3. This is not, it would create R3 because that is not possible. It would create an R3. This is the way that you can kind of like think about it. Okay. Does that make sense? So in like a picture form, let's say you start in this circle. Okay. So these are where all your x's live. X lives here. Okay. This bigger, more misshapen blob, this is where B's like technically like live, like how many entries they have. Okay. This is where we can actually get to, this little circle. Okay. So this circle is our range. This circle is our codomain. Okay. Because it's within, our range is within the codomain. Okay. And this is our domain. It's a little tricky to think about it and stuff like this, but this is more like technical. Okay. But this is like this right here is how you will always find it. This is always true. Okay. Cool. So from here, let's talk about column space, null space, and then orthogonal column space and null space. So let me pull up my notes so I don't say the wrong thing and confuse y'all. All right, so I'll leave that like hinted at right there. So what is orthogonality? What the hell is it? Think of it as perpendicular in a higher dimension, okay? So that's like the only definition of it. For those of you that have to take multi, you'll be seeing that a lot in there towards the first unit. It comes up in a lot of different maths, and if you're mechanical engineers or most different types of engineers will see it a lot going forward. Because we're talking about 3D space for a lot of stuff. So think like my iPad is a plane, okay? It's just some plane in space, all right? What is perpendicular to it? It's whatever is sticking straight off of it, right? Okay. That is technically orthogonal because it's in 3 space. But since we're talking about vectors, okay, they can't just be anywhere. They have to be starting at 0. Okay. So to like branch it off, let's talk about, oh God, can I draw a 3D plane? Okay. So let's call it X, Y, and Z because it's not always super intuitive. So let's say I make a plane on the XY plane, okay? And I have a vector that shoots straight up the z-axis, okay? It is orthogonal to it because it sticks straight out of it, okay? Now what that means mathematically, what they'll tell you in multi is the way you can think of orthogonality in 3 space is if you're like if this is my plane, I am like immediately looking straight down onto it, okay? So they like to draw this like super big flashlight shining down everywhere, okay? So if I'm like looking straight off of this table at something that sticks straight up, I'm going to see nothing, right? I'm going to see a single point at 0, and that's nothing, okay? That means it's orthogonal, okay? So vectors can be broken up into different components. So let's say instead of a vector like that, we had a vector that came more off to the side, but still had like some component of z, all right? So how do we describe this? We'll call this u, okay? So we can describe it into the parts that go in the direction of the plane and the parts that go straight off, okay? Like we draw a line straight down until it hits the plane, okay? And then we just draw from the origin to there, okay? So this is the projection of u onto our plane w, okay? That's what this notation means. And this is the orthogonal component, the part that sticks straight up, okay? This only makes sense if we're talking about a space or a subspace, right? Yeah. So that's how you like break it up, okay? So how to calculate that, we will get there. But to first talk about spaces for a column space of a matrix A and null space of a matrix A, all right? Column space of A is the B's that you can get, okay? So you can think about it like in terms of like verbiage as what B's can I get? Okay. So this is talking about like your range and your codomain. Said what is the horizontal line? The horizontal line is the projection right here. Like this blue line here sits on the plane. Okay. This one. And then this one sticks straight off of it. Okay. It's hard to draw 3D and 2D, but I'm trying. And then columns or null space is your solution set to AX equals 0. All right. Cool. So those are the definitions of what those are. In terms of how to find it, to find column space, to find a basis for column space, you row reduce echelon form A, take respective pivot columns. Okay, so like if you have a matrix that looks like this in reduced row echelon form, okay, and let's say it was okay. So this tells us we're taking this column and this column, so our basis for the column space of A would be this and this. Okay, not this because there is no pivot. All right. For null space, we find the solution set. So once again, we row reduce echelon form A. Let me put it in parametric form. Then from the parametric form, you take the vectors. This is how to find a basis for these spaces, okay? The dimension is just how many linearly independent things make it up. So it's your number of vectors for null space, and it's your number of pivot columns for your column space. Okay. And we did an example of parametric form a minute ago in terms of like eigenvalues and stuff. But now we move away from just A and null space of A, we move into the orthogonal components, okay? So for like a line, damn, that's really ugly. For this line here, okay, what does the orthogonal space looks like? It looks just like this. A line that is, since we're in two space, we can call it perpendicular. So this is our W. This is our W orthogonal. Okay? That's what it looks like in terms of this. If we move into a higher dimension, like we were, okay, and we're on this plane here, W, okay. W hat goes right up and down the z-axis, okay, or whatever axis we call this, okay. It's the whole span of those vectors, all right. So RA are the rows with pivots. Yes, I'm getting there. The orthogonal projections have to do with eigenvalues and spaces. Yes. So rule of thumb, when you are projecting, you always, always, always know your eigenvalues right off the bat. Okay. If you are just projecting, you know your eigenvalues. All right. It is similar with stochastic matrices, which I'm sure we're going to get to. So for all projections, what are your two eigenvalues? 1 and 0. Yeah, always, 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 always. If you see projection right off the bat, you know this is true. Okay. If it says projection and a rotation, that is no longer the case. But for just a strict projection, this is always the case. The multiplicity totally depends. So your multiplicity of 1 with multiplicity, this is algebraic because they're eigenvalues, of dimension of W. Okay? And whatever is being shoved to 0 has a multiplicity of dimension of W perp. Okay? So going back to this example over here, right? What your space and the space orthogonal to it should always add to this total space, right? If you have a two-dimensional plane, you know you have a one-dimensional perpendicular space, orthogonal space. If I say perpendicular, just assume it's orthogonal. Same thing. Yeah, so like in this, we have a plane and we have a line, right, as our orthogonal space. So that means like for our eigenvectors, they're the vectors that are on this line, okay, for lambda equals 0. And on any two linearly independent vectors that construct the plane are our eigenvectors for lambda equals 1. But it's important to note that, again, space plus orthogonal space is the whole shebang that you're in. Like here, we're in R3, right? And W is an R2. W orthogonal is R1, right? 2 plus 1 equals 3. Always true. If they tell you the dimension of W, you know the dimension of W orthogonal. All right. So now going to our orthogonal space stuff. So it's tricky, but essentially what you have is for the column space of A orthogonal, right? it is equal to the null space of A transpose. I'm going to move this to a space that's a little bit clearer to see. Okay. To find the column space of your orthogonal stuff, take the null space of A transpose. Okay.
Why do you transpose? Okay, no. Okay, never mind. You go on.
Okay. For the null space of A perpendicular, it is the same thing as, they write it as the row space of A, right? But the row space is the same as the column space of A transpose, okay? So you can think column space orthogonal just means null transpose, okay? That's the equivalence you can take. It says column orthogonal, that means null transpose, okay? I can go into why that works, but that is a bit of a long spiel, so we can just move past it. Email me. I can help explain it to you. Post it on Piazza. Email your TA. Do whatever. Cool. Does this make sense? All right. So going back to this picture over here, right? What we're doing to this U is we're breaking it apart into two different parts, okay? We're breaking it into a projection of U onto W. That's how you read it, okay? Plus U orthogonal, right? So this part here plus this part here just gives us our original U vector, okay? So how do we find the projection of U onto W? There are a set of equations that you guys can use. If it is a line of best fit, you can get close. But one of the big equations to learn that will be probably one of the most important equations you learn in this class going forward is to project onto a vector, okay? There's a simple computation and there's a matrix you can use, okay? So for a matrix, okay, U transpose over U dot U, okay? This yields a matrix such that when you multiply, like, let's call it A, so AX is the same thing as the projection of X onto U, all right? Okay, and for just a simple computation, oh God, what is it?
I'm sorry, for the matrix equation, is the numerator U times U transpose over U times U?
So it's a dot product there.
Okay.
So essentially this will give you like some matrix of 1 over a number outside. And then that's your entire matrix. Factor that in. Does that make sense?
I have a couple questions on the practices. Can I ask them?
About what?
Okay.
On the practice?
It's with
Yeah,
the, it's actually an overlap.
It's
What?
over this? Okay. So which question is it? Just so I can see it.
It's question number, wait, give me a minute. Thought I had it here somewhere. Yeah, so I got stuck on, let's see if I find it.
Okay, well, you're finding it. Just send it in the chat.
That's 36.
Okay. All right, we will get there. But for right now, computation. So I believe if you're projecting onto U, projecting X onto U, it is, oh God, let me make sure I have this right.
Oh, why it's a thing, it just is.
There it is. Okay. Okay, so it is X dot U over U dot U. Okay, so this is a number over a number. Okay, times your vector U. Okay, this is the same thing as just like a computational. Like this is only for a line, a vector. Okay, so if it says like the span of a vector, this is what you do here. Okay. All right, cool. So going on to this question, question 36. Insert second. Is that the wrong file? No, it wasn't. All right. So for this one, it gives you a plane, right? So it's for the orthogonal projection onto the subspace. Okay, so we're looking for the projection onto W. All right, so that's what it gives you here. We're projecting all things in R3 onto this plane. All right. Okay. So, if we're projecting everything onto this, we're looking for the one eigenspace. All right, and the one eigenspace is the stuff that is not changed on a projection. It is the stuff that already lies in the subspace, right? If I am projecting onto this line here, and I have a vector that already sits on this line, when I smush everything onto the line, absolutely nothing happens to it, okay? And if nothing happens to it, it's the same thing as saying 1 times x, okay? When you project, and you use a projection matrix, it is the same thing as multiplying by 1, so it's in your one eigenspace, okay? So if we're projecting onto this plane, what we're looking for are the vectors that construct the plane, right? So this is what it gives you that construct the plane. So what is this? This is a null space. Another cool rule of thumb about subspaces, if they ask you a question, if you can write the operations they give you in a matrix, and it's equal to 0, after you do like variables on one side, numbers on another, it has to be equal to 0, then it is a subspace. Okay, so in this case, we know it's a null space because we have an equation equal to 0. So we can write this as 1, negative 2 times x, y, z equals 0, right? So this, by definition, is just the null space of this matrix here. So again, if you can write something in a matrix form like this, automatically you know it's a subspace right off the bat, okay? But that's not what this question is asking. That's just a little bit more of a review, okay? And again, we knew that it was this since we were talking about the one eigenspace. If it was the 0 eigenspace, we would find the two vectors that construct them, find whatever is orthogonal to it, and it would be some variation of one of these things, okay? If like all of these are numbers, like they're like, which one of these like vectors is an eigenvector for lambda equals 0? So you take your two vectors from here, and then you just dot each of them with that, and whichever one equals 0 is orthogonal. All right.
So is the reason we can come up is the reason we can put in the like 1, -1, -2 vector, is that because like we're mainly dealing in the subspace W, so we can just like take that straight out of the condition equation they give us, and then
well,
that
if you're
just
projecting
happens.
onto it, yeah, if you're projecting onto it, like think like, hey, this like notation is just telling you to construct a plane, okay? So from like this plane, the like directions, like it's not saying like the space W is the orthogonal projection. It's saying like this is the plane we're projecting onto. So it's asking you to find whatever vectors. But yes, since it's a subspace, we know we can describe it in a matrix form. That is true. That is why we use linear algebra. So if we can describe it as that, we can put it in some form of notation or what have not, so that we can do stuff like this. Okay, does that make sense? Does that answer your question?
Yeah, I think so.
Okay.
I had a question about why the one eigenspace, the part that where it says one eigenspace, how that like correlates to this question again.
Yeah, so since it's an orthogonal projection, right? The one eigenspace is when we do this projection, it only changes by a factor of 1. And if it only changes by a factor of 1, it's not doing anything, right? So it's the vectors that sit on this plane, okay? And this plane is constructed by this equation, okay? So whatever lies on that plane is in our one eigenspace, okay? Does that make sense?
what happens if it gives it a
If that
different
makes sense.
eigenspace instead?
If it's a projection, it's only going to be 1 or 0.
Okay, if it's 0, then what will the answer be then?
It would be numeric. Like these would all be numbers of things. They would just be like different number vectors. You would get your 2 vectors that construct this plane. So let's call it 1, 1, 0 and 2, 0, 1. Okay. These are just 2 linearly independent things that construct this, right? 2 linearly independent answers. All right. It doesn't matter which ones you pick, okay? It doesn't matter. That part doesn't. But whenever you take the dot product of like this, not like null space of a vector, it would just give you like 1, 1, -1, 2, 2, 1, 1, 1, whatever. What you would do is you would just dot this with both of these, and if it's 0, it's in your 0 space because it has to be orthogonal to that, right? So if it's orthogonal, the dot product is 0 because the dot product describes how parallel something is. And if it is not parallel, its dot product is 0. Okay. Cool.
Just in general with orthogonal projections,
Mhm.
when you're looking at the one eigenspace, you're looking at null, like the answers would include null, and if you're looking at 0, it would just include the vector.
Yeah, 0 would be like the vectors that are orthogonal to your null.
Okay.
Because like to construct a plane, like you can't just give like, oh, construct a plane such that like x minus y minus 2 with nothing over here. Okay.
Yeah.
And if this were equal to 4, okay, then it's not a subspace and this question is garbage.
Okay. Thank you.
Okay. For the matrix part that was discussed, is that also used for given just line? Yes, that is also true. I see 36 and I see 20, so we're going to go through those.
Before you do 20, I have a question about this one.
Yeah, go ahead.
Why is the 1, -1, -2 sideways?
Oh, because it's a matrix. Because like remember like towards like the very beginning of the semester, when we wrote like initially, this was like this is our variable vector, this is equal to b, b is whatever or like our numbers are, right? Like equals like 3 equals 2 equals like when you plugged in an equation to a matrix, right? In like an augmented form, this would be 1, -1, -2, augment with 0, right? And if you had another equation, it would go right under it, right?
But we don't have another equation.
You do not, no. So if they gave you 2
Null
equations here,
is always horizontal, right?
It's just whatever your vectors are, or it's whatever your matrix is. But for this, like your matrix is horizontal because it's one equation. Okay. All right, so I'm going to go through 20, and then I'm going to go through 36. Courtney.
Yeah, also 34 as
Yeah,
well.
go ahead. Go ahead. What'd you say?
Oh, can we also do 34 later? It's like similar questions. Yeah.
Yeah. I see that. 34. So I'm going to do 20, 36, 34. Okay. At any point, if you have any questions, ask me. Cool. So 20. I think I just did a screenshot of that. Let's find out. All right. Let the 2 by 2 matrix that reflects vectors in R2 across this line, okay? So if it reflects right off the bat, which eigenvalues do we have? If it reflects, not if it projects.
Isn't it 1 is an eigenvalue?
Is it 1 and -1?
It is 1 and -1. That's correct. Because like whatever you're reflecting over, like let's say we're reflecting over this line U, and we're going to pretend that it goes through the center, and I drew better than that. Like whatever it is, you can't like break down anything numerically. Like this is always going to be times 1, and this is always going to be times -1 as you reflect it. Okay? No other number is going to be reflected by a simple amount of like a number. Which actually, the reason we have complex eigenvalues is because they denote both rotation and expansion or compression. That's a question for a different time. But it is very interesting, and that's the whole reason that we use complex. It's not because we're really dealing with complex numbers. It's because we want to keep things in two parts so we can show both an angle and a magnitude. That's a little high level. It's okay if you don't totally understand that. But so for this one, what vector constructs our one eigenspace? So it's anything that sits on this line. So let's choose x1 to be any non-zero number. Let's choose it to be 1. All right. So what does this satisfy? We plug in x1 as 1. We get x2 to be -4. Cool. What do we know about something that is perpendicular to this vector? What we know is if it's orthogonal, if it's perpendicular, the dot product is 0. Okay? So, I can... Did I do that wrong? One moment. Is 2, 1. Why would that be true? Oh, sorry. I'm totally reading that backwards. I read it as VI as the answer, but it's definitely IV. So, which one of these dot products, like which one of these dotted with 1, -4, this is our lambda equals 1, equals 0? You can check real quick. So, remember that for dot products, it is like the intuitive matrix math, right? So like you have ABC dotted with ABC. It is A times A plus B times B plus C times C. Okay, intuitive stuff. So we can go through these really quick until we find one that's 0. For the first one, 1 times 1 is 1. -4 times -4 is -16. Add them together, that's 17. Non-zero, move on. 2, similar, gross, pass. For 3, 4 times 1 is 4. -1 times -4 is +4. So 4 plus 4 is 8. That's not 0. That is not orthogonal. For number 4, for IV, okay, when we have 4, 1 dotted with 1, -4, okay, this gives 4 times 1 plus 1 times -4, which is 4 minus 4, which is 0. Therefore, this is our eigenvalue of -1. All this goes around to say that... Huh?
I have a quick follow-up with this. If it said the eigenvalue was equal to 1, would you just list an eigenvalues on like the line?
Yeah. So that'd be this. This is your lambda equals 1.
Okay.
And this is your lambda equals -1, or any scalar of it. Okay.
So do you?
Go ahead.
Oh, so do you know you want the dot product to be 0 because it's asking for the lambda equals -1? Is that why? Okay, thank you.
Yeah, because we're talking about a reflection, and you know that they're orthogonal for all projections, right? Because it has to be something like, if you're reflecting over this plane, if it's sticking straight up, it's just getting multiplied by -1 every time you reflect it. So that's how that works. Cool. So moving on to 36.
Oh wait.
There.
How do you know that the initial vector is 1, -4?
Oh yeah, you literally just plug in points here. It can be any like scalar of this. If I want a -1 to be, I don't know, pi. So let's call x1 pi. And when we plug it in here, we get x2 equals -4 pi. Okay, totally the same thing. You literally just plug in a value and you find the other one accordingly. Okay.
Is it just a fact that when it's like a reflection across the line, the eigenvalue is 1? Or how did you know that?
Yep, that's exactly true.
Okay.
Things that sit on the line are 1. Things that are orthogonal to the line are -1.
Oh, okay.
Similarly with like a projection, if it is on the plane, it has a lambda of 1. If it is orthogonal to the plane, it is a lambda of 0.
Oh, okay. Okay.
Cool. Those are the two really big facts you guys need to know. And if it's a reflection, you know right off the bat, it does not have any real eigenvalues. If it is only a reflection.
So is the -1 eigenspace, is that the part that is orthogonal to the plane?
Correct.
Yes.
Yeah, good.
Okay. Thank you.
Cool. 36.
Really quickly, you just said that reflections can't have any real eigenvalues. I thought there was like something we did during class that had like a real eigenvalue. It was like it had like plus minus I and it also had 1 as the eigenvalue as well.
Say that again?
I think there was something we did during class that like
Mhm.
I for like an eigenvalue, and then it had like also 1 plus or minus I.
Yeah, so that means it like if it's pure reflection, it's not going to have a real component. But
So
if
if you
you're
have
in
like
3D, you can think of it as like you can only reflect like so many ways in 3D, right? So something is always going to be orthogonal to it. So that's why they come in pairs also. Geometrically, that's the reasoning for it, that they come in complex conjugate pairs. Hopefully that makes sense. That's a little like over the top explanation of all of this, but regardless. So we actually already did 36 as well. I believe that was, yeah, that's that one. So I moved to 34. Oof. All right. So the orthogonal projection span the matrix for the orthogonal projection onto the line spanned by 4 or 3. So what is the formula for this? U transpose over the magnitude of U squared, which is the same thing as U transpose over U dot U. Okay. Yeah. So what do? We plug in U as 3, 4. So we have 3, 4 multiplied by 3, 4 over dot product squared, which is 3 squared, so 9 plus 4 squared, 16. Okay, and this product, I'm doing my matrix math up here because I'm a little lazy. 9, 16, 12, and 12. So this is our matrix with this part in the bottom as well. So this is 1 over 25, 9, 12, 12, 16. Okay. So that is just an application of the formula for that one. So for future classes, a thing to note, you will see this version. Okay. For right now, you're seeing this one. Know that they are equivalent. Okay. For multi, like you're going to open the class with vectors, you're going to be doing this stuff from there. When we use the equation A transpose AC equals A transpose X for the equation of orthogonal projections. So that is one of the other ways we can find it. But in this case, we're only given a line. If we were given like 2 vectors, let me think actually. A transpose X. We are given X. Yeah, this is if you're given a single vector right here. But when we use A transpose A times C equals A transpose X, that's for like a line of best fit. You can also use that generally for other stuff. You technically could use that for this, but what you're going to have to do is that's going to give you some kind of X, okay, for a given B, okay. It's going to give you an X hat, then you're going to multiply a X hat back into it to get X. That's for the question in the chat that says, when do we use A transpose A X equals A transpose B? This is if you are given a B. This is when you're doing a particular thing. Doing this is for just the general big picture stuff.
So with that, what is the difference between finding the AX hat and just finding X hat?
So this would be like, X hat is like for your line of best fit kind of stuff. If it's you're given like A plus BX equals Y, your X hat is going to be equal to AB. Okay. For any like, oh god, let me think. And then going, you don't usually use it for like best fit stuff. per se, but the closest thing on this is the x hat that gets you your AB. If you were to plug this back in to like call it your big matrix, we'll call it A tilde. Just think like the different matrix of all like what you construct from there. A tilde x hat, this gives you the projection. Okay. B. Okay.
What's the sign you put above the A?
It's a tilde. It's just meaning to say that this A and this A are different. It's not like standard notation. It's just saying like I'm denoting it as something different.
So if we were asked to find like the general matrix for the projection, would it be better to do the other one? And then like if we're asked to find the projection, would it be better to do the first one? Or would they both, do they both give you the general, like the matrix for the projection?
So this gives you the general matrix for a line.
Right, okay.
This gives you this for a matrix and a given B. Okay.
Okay.
So this is like, think of this as like particular, and this is general. Okay.
Okay.
And there's also the monstrous equation I believe you guys have seen. I believe it looks like that. To get your general matrix, right? That is a gross equation. If you're not going to be given anything like, oh, here's two 4x4s, like do this, like but this will like if we were to plug in like A equals 3, 4 into this, I believe we would get the same thing as that. But this is discussing, and you shouldn't do it unless you need to.
Okay. Thank you.
Yeah. And then this, again, is for a particular B. Okay?
Okay. So if not given a B, then we have to use the other one.
That is correct. Yeah.
Okay.
For those of you who are taking differential equations next semester, this is coming back. You're going to be doing a lot of this junk. Yeah, fun stuff. All right, I see 22, see 29, 19. Did we do 19 yet? No, we haven't. 19, 29. Oh God, my rating is so bad. I'm so sorry. 19 to 29 to 31 to 22 is what I have right now. I may be looking over stuff. I see 28 as well. Okay. We'll start with 8 because that was the furthest back. And 28 on the reading day. I'm not going to go into all these in super heavy detail. Hopefully if one of them covers something similar to what we've just talked about, maybe you could post it on Piazza and get a little bit better of an explanation. Let's see. Where the hell do I find the reading day? Was that the link sent in the chat? No? Okay. That's on the course calendar, right?
I can send it the link on the chat if you need it.
It's okay. I think I have it right. Yeah, there it is. Okay, so just while I'm like thinking about it and have it up. Yeah, so 28, briefly. This is a rather quick question. This is just talking about some definitions of eigenvalues. Come on. Yeah, so here we have, hey, given x is an eigenvalue, x is an eigenvector with lambda equals 3. And for b, lambda equals 4 for x. Here we're applying some, like it's asking what is this, right? So the way you find this is you distribute. So 2a minus b x equals 2a x minus bx equals, oh, it's asking if it is an eigenvector. Okay. So 2 times 3x minus 4x. Okay, so that is 6x minus 4x equals 2x. And since this whole matrix times x is equal to a number times x is an eigenvector of that, of this as well. Okay, this is not always true. In this case, it is. Okay, you just have to check. All right.
So if it weren't true, what would it look like?
It would look something like, let me think. Is not always true? No, it is. Okay, so you're not going to see this very often. You're going to need to check it in general. But if x is an eigenvector of both of these, then it'll be true. Okay, don't generalize that too hard. Just do this math and check. It's pretty straightforward, right? You're just plugging in some numbers and seeing if it's still a number. In some other cases, you might get in this case, they give you the same x. If it was check if this was u and this was v, and you got something that looked like 3u plus 2v, right? It's a different number with u and v, so u plus v would not be eigenvector. This is for a totally different set of questions. Yeah, so a little tricky. But I believe since x is an eigenvector of both, you know it's an eigenvector of all linear combinations of the two. That's not something that you should write, note, memorize. That's just a plug in and figure it out kind of thing for the most part. You're not going to really see just a general, hey, is this, yeah. So it's 28. Moving to 8 itself. Ooh. All right. This one is also, thankfully, a little quick. It's just knowing a trick, which is a little confusing, but that's okay. Okay. So, how we write this is we're taking the linear transformation of x1, x2, x3 to get us this gobble here. So, how do you find the standard matrix? You write it, ax equals b, right? So b equals 0 to x1 minus x2. Oh, it's 4 entries. That's okay. x2 minus 3x3, x1. All right. So we are starting in 3 and ending in 4. So we know this is a 4 by 3. Okay. That automatically crosses off 2 of your answers. All right. Now, what you can technically do is you can just generally plug in x1, x2, x3, and see which one of these results in it. But a little bit of an easier way to think about it is we simply just read the matrix by row. So in the top, so we go row by row. So in this top row, and in this answer, in the same row, how many x1s are present? 0. How many x2s are present? 0. x3, 0. For the second row, okay, corresponding to this answer, how many x1s are there? 2 x1s. How many x2s? -1s, -1. And how many x3s? 0. Okay. Then you go to the next row, you get 0, 1, -3. And for the bottom one, you get 1, 0, 0. So that gives you A as your correct matrix, or this as your correct matrix here. Okay. Questions on that? We actually did do 19. So 29. Cool. So this is going back to some definitions we talked about. So I'm just going to write it. Let A equals 1, 2, 3, 4, 5, 6. Okay. What is basis for null of A orthogonal? Okay. So basis for null A orthogonal is the same thing as the column space of A transpose. Okay. So now we're finding the column space of A transpose. And remember, for transposes, keep the that's ugly. Keep the main diagonal the same and reflect everything else across it. So we have 1, 5, 4, 2, 3, 6. Okay. So what you're going to find is these two vectors here. So now this is just a column space problem. We're finding the column space of this matrix. And you're going to find that these are two linearly independent vectors. Therefore, basis for null of A perp equals basis for column of A transpose equals 1, 2, 3, comma 4, 5, 6. Cool. So this is just like knowing the definition of this. Okay. And again, pretty straightforward. Switch null and column. Switch this. Think of it as just an upside down T. So you switch both of them. Okay.
I have a question.
Yeah.
To get A transpose, could you just make the rows into columns? Is that the
That
same?
is the definition of what it is. Yeah.
Okay,
It is exactly
thank
the same
you.
thing as what I did. It just like for like some higher level stuff, it's just a little easier to like, you can get a little confused with yourself. So I just think of it as like across the main diagonal, or you like pinch this right here and you pull it over to the top right corner. A million ways to think about it, a million ways to write, totally okay. All right, that was 29. No, 29. Now we're gonna do 31. 31. All right. It's a little messy, but that is okay. It's not hard. It's just a little bit computation. Normally, y'all's final would be 10 questions. This would be like if we were like having an in-person finals and stuff. The way 1553 used to be is 10 questions of everything throughout the course, and the last one would always be a least squares problem. So solve least squares with the exact same formula, you always do it, and most students manage to get it right because it's just an application of formula. Another thing I'll say about something that you've probably noticed about the exams in this class and about the exams and that you can assume about the final, they're not going to ask you like, hey, here's like this like 8x3 matrix, find the least squares of it. Right? That's kind of crazy. There's a lot of room for error there. They're not going to give you anything where there's too much room for error. If there will be, it'll be like parts at most. Okay? It's not going to be like, oh, here's like a single number block where like it's all or nothing kind of thing. Okay? Which is good for the most part. It's trying to give you as much partial credit or break down things into like their little components or definitions. So hopefully that is advantageous to you. But we shall see. Okay, so right off the bat, subspace convect of all the vectors of the form. Right, so.
A quick question. Can you make it a little bigger on your end?
Oh, yeah, sorry.
Thank you.
I know Blue Jeans makes it a little bit blurrier and like worse to see. So, yeah. Just always say something if that's ever wrong. Thank you. Cool. So, what do we know? What do we know? If it is orthogonal, what is its dot product? 0.
0.
0.
Yeah, 0. Always 0. Okay, so remember to dot something, they have to be the same dimension. Okay, so this is gone. Boom. Those are 3-dimensional vectors. We're talking about a 4-dimensional vector. Annoying, gross, bye. For the first one, you can pick any one of these. Let's pick this one, all right? This dot with this is we'll call this v. Call this u1. u1 dot v is equal to x plus y plus z. Okay, and this is for all vectors. So is that always equal to 0? Wrong. For the second one, what you're going to find is for u2, we'll call this vector u2 dot v is equal to x plus y times 1. Oh, negative 1 plus x plus y. So that's pretty clear that that is equal to 0, and that is your answer. You can try for this one and either of these, and you're going to find that even though for case E, when this one is not. So this does not form a basis. Okay.
Is there a way to know that
You just do the transpose of and then row reduce?
Oh.
Yes.
Oh. That works too?
I think.
I got the same
This
answer,
is supposed
but
to
I
be a
didn't do
dot.
it that way.
This is supposed to be a dot operator question, but I believe that is true because basis for W perp is the same thing as the column space of the orthogonal, which is the same thing as the null space of the transpose, which if you row reduce it, put it in parametric form and get your vectors, yes, that is true.
Okay. Because yeah, I didn't do this way. I did that way.
Okay. Did you get the same answer?
Yeah, I got the same answer. That's what I was wondering.
Yeah, then yes, it is the same thing, but it's just a matter of personal preference. If you want to do it like that, or if you see, like, find a basis, you can just check if they're equal to 0.
Sorry, what's the same thing? Can you repeat that again?
Yep. So for this, you can, like, take this matrix and call it A, all right? And we'll take out our vector, all right? So this is going to be 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0. Okay? Times your x vector. Okay? So if we take, since we're finding a basis for W orthogonal, so this is the same thing as the column space of that. Or I guess now we'll call it A, same thing as the null space of A transpose. And when you find that, you're going to find the exact same vectors we talked about. But this whole computation can be a little trickier, and you have to do some row reduction and stuff. The easiest and fastest way to do this is with dot products. Because if this was like some like bigger thing where they had even more like variables and things, it'd be like they were nice enough to give you ones, negative ones, and zeros.
Can you just, I think other people have the same question. Could you just like explain the dot product of what you dotted just real quick again?
Yep. So the way you do it is you take this vector. You can dot symbolically, remember that. So remember a dot product is just it's just some number that means how parallel it is. The bigger it is, the more parallel. The smaller it is, the less parallel. If it's 0, it's not parallel. And if it's not parallel, it is like not in the direction at all, which means it's orthogonal. Okay, so think of like how parallel corresponding to the projection. All right. So for this first one, we can pick any of these 4 vectors or any of these 3 vectors. Okay, and if it is a basis, then each of these vectors dotted with this will be equal to 0. Okay. So u1, u2, u3, each of them dotted with our vector v will all be equal to 0 if that is true. Okay? Since it's not, we know it's not. For the second one, we check u1 dot v. This is equal to 0, therefore it is a basis of W perp. Yeah, but you have to make sure you check all of them, technically. Like, you can ignore the other stuff that, like, is no way to form. But, like, if by some manner, like, this one happened to be orthogonal, and this one happened to be orthogonal, like, both the dot products were 0, and they were not scalar multiples of each other, or linear, or technically, since there's 2, linear combinations of each other, then this would be your answer. If both u1, u2 dot v equals 0, and u1, u2 linearly independent. Okay.
So you would dot u1 and u2 separately, and then if they both are 0, okay, got it.
Yeah.
And they got to be linearly independent, because if they're not, then
yeah. Otherwise, it's not a basis because it's not.
Okay, that's the basis. Okay, got it.
Yeah. Cool. Oh God, where the hell is my list? That was 31. Let's look up 22. Do you guys understand stochastic matrices? Is that good? Any questions on that sort of stuff?
Can we go over dampening? Is that important? Like dampening?
It is. Not especially for this, but conceptually it is rather important. I do not have the formula with me handy, but actually let me do 22 first, and then we'll... Is there a stochastic matrix question in the practice at all? Could someone find
on
that
the
and send it to
practice
chat,
final.
please?
I know.
Yeah, could someone find the number for me and send it in the chat? I'm going to do 22 really quick. Oh, good lord. Oh, no. Oh, this is a stochastic matrix question. There was just so many numbers that it looked gross. Okay. So, no, damn it. Please be the right one. Oh, shit. Did I say 22 or 23? Oh, I said 22. This is 23. We'll go over 23 in a second as well. Yeah, so 22. I'm not going to write it, but we'll just talk about it for a second. So this question gives, hey, let A be 3 by 3, and suppose the null space is a line. Okay, so null space is a line. Okay, and ax equals x for all x in the subspace. So that ax equals x means ax equals 1x. These are eigenvectors for lambda equals 1. All right. And you'll note that it's a 3 by 3. So we're looking for 3 total vectors. Okay, right? We need 3 eigenvectors in order for it to be diagonalizable. Okay, so we know the null space is a line. That's 1. And for this, it gives us the subspace W. So you'll notice that it is x1 minus x2 minus x3. So in this case, you can construct 2 linearly independent vectors from that. Or you can technically take the null space of the matrix it composes and then put it in parametric form. Or you can look at it and you can say, hey, this is 2 free variables. Therefore, it has 2 linear independent vectors, and therefore it has 3 eigenvectors and it is diagonalizable. Okay? That's how 22 works. It's a lot of definitions juggling around each other. All right. Questions on that? I know it's a lot of words and it's kind of boggling to just kind of like say it and like listen to it. But hopefully it's making some sense. All right, 23. So this asks, what is the steady state vector for A? All right. So a steady state vector is by definition when A times our vector is just equal to our vector again, right? Wherever our people are set up, whenever they shift by some amount, the same amount of people are in there. Like whoever left, that amount came back from other places. That's why we know for all stochastic matrices, there's always a lambda equals 1. Okay? So what is this right here? This is taking the null space of A minus lambda I, which is finding the eigenvector for A minus lambda I. So that is the definition of how to find your steady state vector. Okay? So, a reminder that we're talking about probabilities here. So they can't add to be more than 1, right? You can't have more than 100% of people by column, right? So just as a note on the side here, for stochastic matrix A, okay? If you're given a bunch of like different, like, hey, these people start here and go here, these are where they start. start at, call it 1, 2, and 3. This is the people that end at place 1, place 2, and place 3 accordingly. All right? So if everybody, if 50% of people stayed in 1, 25% of people stayed in 2, and you don't know how many people stayed in 3, yes, you do, because the column has to sum to be 1, so you know it's 0.25. Okay? If everybody who's in 2 goes to 2, right, they start at 2 and they go to 2, that'd be a 1. And if people split evenly going from 3, that's all 1/3. Okay? That's just like the definition of like how we construct a stochastic matrix. And then A minus lambda I, we find our eigenvector for that, and that is our steady state. But reminder that our steady state vector has, like, all the components have to add to 1, right? So like right here, okay, this is telling us, hey, this is some form of our steady state vector, okay? Do they add to 1? No. So what do we have to do? We have to divide by the sum. So what you do is 1 over 18 plus 21 plus 13 times our vector gives us steady state. Right, so it is not this. These are not the form. We do not need more information. We have been given enough information. It is not this one because it is not equal to 1. The sum isn't equal to 1, so it's this one. All right? And then for B, what this is asking is, hey, as we have this many people in these many places, what happens? So regardless of how many people, like where you put them and stuff, as you go to infinity, like it always approaches steady state, okay? Even if like one person trickles out each time, it'll always like leak out after you like do like your rotate, you do your like your whatever your steady state does that many times. So we just need the total number. So the total number is the sum of 48 plus 2 plus 2, so 52. Oh my god. 52, okay? And how do we find what vector it approaches? We take that number and we multiply it by our steady state. No. 52, 18, 21, 13. Wow. Look how easy they made it. Done. Cool. So the question is damping, right? What the hell is it? So damping is essentially like you're trying to like mitigate things so they don't explode. This doesn't really like apply to like those fun little diagrams that are like, hey, 20% go here and 60% go here and you know whatever else, like 20% stay in, right? This is not, we don't use damping here unless we're like explicitly given it, right? So damping is basically like how much we're trying to control it. In like differential equations, we use dampening to define like spring systems, right? Because springs are dampeners and they move something towards like a particular limit. So the goal is to move it towards a particular steady space. I actually don't have the formula on me immediately, but I believe it's a dampening factor of P, right? And it's 1 minus P times A x. Does somebody have the formula ready? Just so I don't like accidentally. Oh, dampening is not on the test. Never mind. We don't have to talk about it. That's a differential equations thing.
Can we still go over the importance matrix part of that?
The importance?
Yeah, because he said that that is going to be on the test, but like the damping factor isn't.
Okay, so when he's talking about importance matrix, is that like this matrix here? I'm not sure what exactly he means by that.
There was an example in,
he just means the Google matrix.
In the test.
Okay.
Yeah, the Google matrix.
Okay. So it just means it's some really, really, really big stochastic matrix, and all of the things for stochastic matrices are still true, I believe. Somebody correct me if I'm wrong on that. That's not something that we really like talked about at any point. Yeah, so basically like if you have Another thing is if you have like a stochastic matrix and it composes like 0.7, 0.30, and you have like a column of all zeros, right? Like no one goes, no one leaves. Okay, what you do is you just 7.30, you just substitute in 1 over the number right there, I believe. Is that correct? Because I know that is something that is noteworthy. Like if in a stochastic matrix, if you have a column of all zeros, you substitute it with that.
In general, you substitute it with 1/3, or is that based on the number of columns?
Whatever the number is. So if like,
Okay.
yeah, the number of columns, 1 over number of columns. So if this is 4 by 4, instead of 1/3, it'd be 1 over 4, 1 over 4, 1 over 4, and then another 1 over 4 down here. And if it's 1 over 5, all these would be 5s, and so on and so forth. Okay.
So why do you do that?
Basically, it's just a mathematical correction that we do. It's kind of confusing, and it comes with like going forward in the class and like stuff like that. It goes with like when we converge to certain steady states. Like you're going to talk about this in WQ when you get towards the end. You're going to have to draw like little like diagrams of like the poles they approach and like how they swirl into them, and this is like that correction. In a matrix with websites, like if website A looks to B. Oh, okay. So an important, okay. Yeah, so if you can find this, and if you're given like, hey, like 50% of people stay in the same place and 50% go here, if you can like, given like those things, construct a stochastic matrix, then you're pretty good with stochastic matrices. And then you can find the steady state. That's just about all you will ever need to know. Okay. And then if you plug things in, where do they go? Obviously, but yeah. Cool. So number 26 is the next question. All right. So I'm not going to write it down because it's a little, there's just a lot of extra words. So you're given A is 5 by 5. And the determinant of A minus lambda I equals 2 minus lambda cubed, 4 minus lambda, 5 minus lambda. Cool. So what are our eigenvalues off the bat? Lambda equals 2, multiplicity of 3, 4, multiplicity of 1, and 5, multiplicity of 1. Because it's just the power that each like factor is raised to. And remember that when you find a characteristic polynomial, so if this was a bunch of numbers written out, like this is like, hey, this is like lambda to the 5th, blah, 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 plus 18 lambda, 2 cubed is 8 times 4, oops, plus 160, something like that. This is your determinant, this is your trace. Those are just always the things to know. For any like characteristic polynomial, it's always plus trace of lambda. I think it's minus the determinant.
Wait, I think it's the other way around.
Oh, it's the other way around? Okay. Minus the trace of A times lambda plus the determinant of A. Right? Cool. That's just a general thing to really help, but some things to know. If something is invertible, what does that mean? Well, it means a whole damn lot of things at this point. Step 1 is check if it's square. So going past that, if it is invertible, it does not have 0 as an eigenvalue. Okay? Because think like projections. All projections have a lambda equals 0. Whenever you project onto a plane, is there an easy way to go back or invert? No. So that's like your like easy example of it. Okay. So is A invertible? Are all lambdas non-zero? Yes. Therefore, it is invertible. It must be invertible, rather. And part B asks, suppose the 2 eigenspace of A is 3-dimensional, is A diagonalizable? All right, so remember for each distinct lambda, you have that number of distinct linearly independent eigenvectors. Okay. So if you have all distinct eigenvalues, you have all distinct eigenvectors, and you know automatically that it's diagonalizable. But in this case, we have, hey, they say, hey, our 2 eigenspace has a geometric multiplicity of 3. Therefore, is this diagonalizable? Yes, it has to be. Because we know for each one has at least 1, so this is at least 1, this is at least 1, and this gives us 3 eigenvectors, 3 plus 1 plus 1. That is a total of 5 eigenvectors. Therefore, we can make it diagonalizable and plug into our C.
So, question.
Yeah.
If that was raised, it's kind of 2 questions. If the first eigenvector or eigenvalue was raised to the power of 4, would that still hold?
It would not.
Okay, that makes sense. And then if it was raised to the power of 2, it would hold.
If it was raised to the power of 2, this would have to be 2, but yes, it would hold.
Okay.
Because you can never have more geometric multiplicity than algebraic. Okay? That's just a rule. They're probably not going to ask you about that, but that's just like, you can't have more eigenvectors than multiplicity of eigenvalue. Okay? The like technical, like written form of it is n is greater than or equal to algebraic multiplicity, which is greater than or equal to geometric multiplicity, which is always strictly greater than 0.
In this case, how do you know that the multiplicity is for the geometric multiplicity, not the algebraic multiplicity?
Because it talks about space. And if it's talking about space, it's talking about geometry. And if it's geometry, it's geometric.
Okay, thank you.
Yeah. Just some fun little verbiage that they throw in. So somebody asked to do 28. So 28 states, given the magnitude of u is equal to 2, and the magnitude of v is equal to 1, okay? And so it says u, v are orthogonal, therefore u dot v equals 0. So how you can think about this, you can just think about it as distributing. So it gives you 2u plus 3v dotted with 4u minus 5v. So, FOIL, first outside, inside, last. What is 2u dotted with 4u plus 3v dotted with 4u? I'm not doing this like FOIL order, but regardless. Plus 2u dotted with negative 5v plus 3v dotted with negative 5v. So right off the bat, we have a v and a u dotted together. So these just go to 0. Okay. And let me think about this for a second. Yeah. So what you do is you multiply your coefficients together and you get 8 u dot, no, u dot u, okay, plus negative 15 v dot v. And we know that u dot u is equal to the magnitude of u squared, which is equal to 2 squared, which is equal to 4. Okay. So what does this give us? It gives us 8 times 2 squared minus 15 times 1 squared, because that is the magnitude of v. Okay. And this gives us 32 minus 15, which is equal to 17. Okay. Questions on that?
So, is the 3v times 4u, that's 0 because they're orthogonal?
Exactly.
Okay, and if they weren't orthogonal, then would you just plug in the values for v and u like you did in the other parts?
You would need each individual component.
Okay.
Like that's why this question is easy. Like it tells you, hey, you got two 8-dimensional vectors you're dotting together. That's hell. That's a lot of work to do it 4 times with a bunch of different like stuff in there. Yeah, but you can always do this right here. You can just like multiply the coefficients and move them over and then do the dot product. So if it says and u dot v equals -1, then from here, like for this one, this would be 12v dot u plus -10u dot v. So like I'm just talking about the two parts we crossed out. Like if they gave you this, okay, this isn't for this question. So 12 times -1 plus -10 times -1. That's how you would do that. Okay.
Okay.
Otherwise, you would have to do it numerically entry by entry, and you'd have to multiply everything, dot it all, combine it all. It's a total headache. Oh, and if you want students to get things wrong very often, you give them simple arithmetic, because everybody messes up on simple arithmetic. But you know what? We're engineers. It's fine. We can do the hard stuff. We have calculators most of the time. I know you don't for this, but regardless.
I also had a question. It's like a true or false statement, and I typed it in the chat because it's kind of long.
Okay. Suppose W is the subspace of Rn and B is the matrix for the orthogonal projection onto W. Then for every x in Rn, we have Bx equals x or Bx equals 0. Why is this false? So this is false because not every x is an eigenvector. If this were to say for every eigenvector x, then it would be true.
Okay.
So like if we have like, if we're projecting onto like this line, right? For like this x, yeah, that'd be multiplied by 1. For this x, it'd be multiplied by 0, yeah. But for this x, it would not. Okay, so this is what makes it not true. If it said for every eigenvector x, then it would be true.
Okay.
That is the little like trick stuff that they're gonna throw y'all with. All right. Okay, I see a lot of different numbers going on in here. 26, 28, 36, 26, 28, 36, 38, 14. Cool. All right, I'm going to try to finish this by 8 because my mother is home and I drove home a couple days ago and I haven't seen her yet. So sorry, but got to do that. All right, so 26. I also was lucky enough to not have any finals, so I've just been chilling, which is very nice. But 26. We did 26. I think that's passed. 28. We just did 28 as well. Damn, I have a really bad memory. Suppose W for question 30. All right, so I was thinking of an easier way to say it, but I'm just going to post this here as well so you guys can read it. And for those of you who are going to be watching this and looking at my PDF, I am so sorry it is so unorganized. All of my notes are like this, and it is genuinely a headache to go back and try to read through the things I have written for myself. But regardless, suppose W is a subspace of Rn. If V is in W, then the orthogonal projection of it onto W must be 0. True or false? That is not true. The projection onto it would be itself, right? This is like our eigenvector stuff. It's saying, hey, if we have a vector that's already lying in the subspace and we project onto the subspace, what is it? Is it 0? No. It is V. It is equal to itself. Okay, that's why that one's false. For question B, it says if B is the matrix of the orthogonal projection onto the subspace, then B squared equals B. This is not as intuitive, but you can think about it in terms of doing something and then doing something again. So let's not think about the numbers behind the matrix. Let's think about what the matrix is doing. So if like I have a line and I have a plane and I mash everything onto it, and then I mash everything onto it again, did it do anything the second time? No, it did not. Therefore, doing it twice, or B squared, which is the same thing as B times B, is just equal to doing it once. Okay? Cool. Yeah, sorry. I'm sure y'all are going home soon. And if you're free tonight, not studying for the algebra, giving yourself a break, there's a group of individuals walking past Britton Rec at, I think, 10 p.m. So it's a little fun little thing to do, so highly recommend that. Cool. What else do we have? That's 30. Let's go over 6. Oof. Honestly, looking over all of this material, this is stuff that I don't think is insanely difficult for y'all to do. I don't think it's anything out of pocket that you haven't covered in like studios or anything like that. So you should not be incredibly surprised by anything on the final, I don't think. And given the amount of time you have plenty of time to think about it, do it computationally. So hopefully it won't be too incredibly hard. I still haven't looked at it yet, but for number 6, right here we're asking what is the null space? How many free variables do we have here? Well, we can row reduce this. We'll know that that goes to 0 because we can just do that. So how many free variables? 1, 2, 3. 3 free variables. 3 free variables. Check. Dimension of row space. Tricky. Dimension of row space is the same thing as a column space of A transpose. Okay. But it is the same thing as the dimension of columns of A. Okay, because this is just asking dimension, right? So how many pivots do we have? 1, 2. Boom. Just trying to be a little tricky on you, but you could also flip it. You could transpose it. 1, 3, 2, 0, -1, 0, 0, 0, 2, -1. Same thing. Not going to write it again. 0, 0, 0, 0. Not a pivot. Not a pivot. 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 2. Done. Cool. Questions on that one? All right. Okay, so here we have a projection problem. All right, 38, yep. W is a subspace of R3, and X is a vector in R3, whose orthogonal decomposition with respect to W is as follows. Okay, what this means, hey, we have a plane somewhere. Okay, here's our plane, all right, and we have a coordinate system. Okay, and we have some vector, call it coming back that way, X, all right? This isn't necessarily drawn in the right directions or any kind of thing like that, but this is just to show y'all like what's going on, all right? So this gives you the projection, XW, and the orthogonal component, XW orthogonal. So what that breaks down to, visually, draw our little line down to the closest point on the plane, okay? This vector here is x on w, and this is x on w orthogonal. Okay? Those are the two vectors that compose x, right? That is a definition that is very, very helpful to learn. And another thing to note, if they ever ask you for the orthogonal part, you just take x and you subtract xw, and that gets you xw there. That is this, which you can find through the multitude of ways that I think we've talked about, like U transpose, or the magnitude squared, or if you're doing your big matrix, that's the same thing. If you're doing least squares, that's the same thing as well. But, so, the closest vector to x in W is, by definition, the projection onto it, okay? This is a definition question. This isn't asking for a lot of numbers here. It gives you a lot of numbers, and it's really and it's like kind of like, oh, okay. But it is just a definition question, okay? So, what is the closest vector to x in W? Boom, it's a projection. What is the distance from x to W, okay? So, the distance is this amount in a vector, right? Let's make that a little bigger. This orthogonal part, right? That's the distance from the plane to where x is. So it's the distance of that. So what is the magnitude of xw orthogonal? Which is square root of 1 squared plus -2 squared plus -3 squared. A thing to note, never more than square. Never, 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 never. Regardless of how many entries it has, it is always the square root, and each entry is always squared. Okay? It is technically called the L2 norm, Euclidean distance. Well, once you get bigger, that's kind of iffy. But needless to say, keep it square. Don't overcomplicate it. If you're given an 8-dimensional vector, don't try to take an 8th root and raise like 3 to the 8th and 8 to the 8th and all kinds of jazz like that, okay? Squares. Okay, keep it easy for yourself. So, what is this? That is square root of 14. Cool. Fun.
What is xw in this case?
Yeah, it is the projection. It is the projection of x onto w, okay? Which is the same thing as, like the closest point is the definition of the projection. Okay. Cool. Questions about this one? That's 38. Now we have, I'm going to write another little chain. We got, I see 14, 29 on reading day, and 7. This is a find an area of a triangle question, okay? Number 14. So it gives you the points -1, 2, 0, 5, 3, -4, okay? The way to do this is very simple. Pick a point, call point 1, okay? Call this one point 1. Pick a point, point 2. Well, we'll just name these appropriately. Point 1, point 2, and point 3, okay? How to find it? You take point 1 minus point 2, and you put it in like a vector form, right? So this would be -1, 2, minus 0, 5, okay? So -1, -3, okay? And then you take point 1 minus point 3, okay? -1, 2, minus 3, -4. That is -4. Okay. Take these two. For a triangle, it's 1/2, the determinant of each one of those two vectors. So you have -1, -3, -4, 6. Okay? Make sure to keep them vertical because they're vectors, okay? And technically, it doesn't matter which points you choose. Like, it doesn't have to be point 1 minus point 2 and point 1 minus point 3. It can be 1 minus 2 and then 3 minus 2 or 3 minus 1. But they have to be different. They can't be the same 2 points twice, okay? Any combination of those, plug them in here. And remember that it's absolute value because it's area, right? But if you get a negative area, you can just slap a plus on it. So what is that determinant? 1 over 2, -6 minus -12, 3. Oh, no, I did that wrong. Minus +12, so it's just -12. -12, so that gives us -18 over 2, which is -9, which doesn't make sense, so we just change it. Because we can. It's the only time you ever do it in linear algebra, but it's nice to do it because it's just like, whatever. That's 14. Okay, so 29, I'm just going to say it. Suppose A is 4 by 4 with 3 distinct eigenvalues, 0, 1, and 2, with 1 having an algebraic multiplicity of 2, which must be true. The first one is A is not diagonalizable, and the second one is A is not invertible. So invertibility is a little easier to talk about. If something has an eigenvalue of 0, the determinant is 0. If the determinant is 0, it is not invertible. So we know it's not invertible. Done. You can just expand that. If you have a lambda equals 0, not invertible. Done. Cool. Which means you have a null space, right? So not diagonalizable. One has algebraic multiplicity 2, but it says absolutely nothing about geometric multiplicity. And what would it have to be diagonalizable? It would have to be 2. But in this case, we don't know that, so inconclusive. So that doesn't have to be true. If it said where the eigenvalue 1 has algebraic multiplicity of 2 and the one eigenspace has a geometric multiplicity of 1, then it would not be diagonalizable. Okay? Yeah, so going back to this, someone asked in the chat why we do the magnitude of x perp. So think if we're looking at this on a flat line, okay? Let's say x and y axis, okay? And the x axis also happens to be our w, okay? So this is our vector v, okay? This is v orthogonal, and this is vw, okay? VW orthogonal, but regardless. So the closest point on this line is clearly right here, right? And the distance is right here. This is easy to see in a 2D sense like this. It is not as easy to see when you're talking about planes that are skewed and crooked and whatever. So this distance here is just a number. It's just the y value. But in 3D, it gives us a vector. So we have to take the magnitude of that vector. Okay? Cool. So where were we? Question 7. Okay. So here we have, we're determining whether each is a subspace. Remember what I said about matrices? Can we define this in a matrix? Yes. We can define it as the null space of a matrix particularly. Yes. Can we define this in a matrix? But the B isn't 0, so we can't define it as a space. So no. You can also think about going through your rules, right? Is the 0 vector contained? Is it closed under addition? Is it closed under multiplication? If we plug in all zeros to B, we do not get 0, we get 4, right? We have 0 equals 4, which does not make any sense. For C, Are those things linear? No. Nonlinear, we don't like it, not a subspace. All right, for the last one, can we write a matrix that describes x, y, z such that x and y are 0? Yes. It's a little tricky, but we can. So we're looking to find a matrix such that z is free, okay? No. Z is free, and we have that such that x and y are both equal to 0, so we just set it like this. So it's the null space of this matrix, so this is. You could also check it plug in all zeros. Is it true? Yes. If you scale it by a scalar multiple, so what is c? Cx is always equal to cy because it's always equal to 0 times 0. Or c times 0 equals c times 0 equals 0, always true. Whenever you add two vectors, they're always going to have the first two parts as 0, right? So when you add them, they're going to keep being 0. So that's how you can think about it, or you can think about it as like a null space. Null space of this. Okay? Cool. All right, we've lost a lot of people along the way, but do you guys have any other questions about anything? Still got another few minutes dedicated to y'all, so I don't want to cut you short, but.
I had a question from a sentence in the textbook. I typed in the chat. It's about least squares.
Yeah.
And so I was wondering if it's like the ax hat equals b column of A, but then it's like also ax hat equals b. I was really confused on that.
Once you have found the least square solution, x hat, then b in the column of A is equal to A. Yes. Okay. So this is saying like a least squares solution, like with your x hat, it's just like the b that exists in your column space. You get there by using x hat. Okay. That's how you get to your projection. Okay. So whenever you find your x hat, a x hat will always get you as close to b as possible, which is the same thing as the projection of b. Projection of b onto the column space of A, onto the subspace A, onto A, whatever you want to call it.
So is ax hat equal to b then? Or does it have to be like b column space?
Yeah, it is the projection. It could be b if b is on that plane.
Okay.
But it might not be.
Okay.
Does that make sense? I hope.
Yeah. Thank you.
Cool. All right. Someone says 10B on the practice. We'll talk about it for a second, and then I will say my good nights. Yeah. So this says the specifications of the dimensions of A and B aren't important, but this says, hey, if B ax equals 0, which must be true, and what is true is we can put parentheses around here and ax in null of b. Because b times this, b left times that is equal to 0. So you can think if like x is in the null space, well, x tilde because it's technically a different x. If this is true, then x in null.
This isn't math related, but do you know if TA office hours ended already?
Totally dependent on the TA. I am not holding any more office hours because mine happened after, but I believe most TAs are still holding theirs. They should, by policy. But.
Do you know anyone who is? Because today I tried going, but no one. TA office hours today? Like off the top of your head?
I don't know off the top of my head.
Okay.
If you have questions, you can email me or you can post in Piazza. I'm going to stop recording now. For all of you who have been watching this, Godspeed today, because I assume you're watching this on Tuesday. So.